Hello everyone, my name is Odhiraj Banerjee. I am an electrical engineering PhD student from IIT Kanpur. Our institute is organizing the 16th Winter School of Speech and Audio Processing. Today is the second talk out of a series of talks aimed to give a brief overview of approaches to audio retrieval. This shall be helpful to all the participants who are participating in the Query by Example and Query by Humming challenges organized by WiSSAP. This talk will be split into a number of videos for the convenience of the audience. In this video, we will present how an audio retrieval system works in real time. We will formally present the problem statement and discuss the search techniques used in Shazam for query by example task. And we will also discuss an approach for query by humming task. Let's suppose you are in a restaurant and you get curious about the song playing in the background. So you bring out your smartphone to search for the name of the song. You open Shazam and record a small snippet of your query. Shazam then sends it to its servers where they have a database of millions of songs. The servers find some K-top matches from the database and sends the metadata of the topmost hit back to Shazam. The metadata generally consists of the name of the song, the start and end times to indicate which portion of the song the query corresponds to. Now we can split each song in the database to short snippets of 2 to 3 seconds and form a database of audio snippets. Now the problem becomes, given a query audio snippet and a database of pairs of audio snippet and their corresponding metadata, we wish to retrieve the metadata M corresponding to our query X. For the case of query by example, the query is just a noisy version of the original audio. So the query and original audio have the same sources and accompaniments, and the query may have some noises based on the background noise or some like clattering of plates, clattering of glass noises, people talking, such types of noises, and also reverberation. For the case of query by humming, the query may be a melody hummed by a person. So it does not contain all the instruments used in the original recording, and it may not also be in the same tempo as the studio recording. There might also be some pitch shift as well. Say like some random person who isn't trained musically singing the song, he might not sing it in a correct pitch, but still we could understand or get a hint of what song he's singing. Now the retrieval is performed via comparison of the query with each audio snippet in the database in some representation space and retrieving the metadata of the most similar snippet to query. As a basic form of retrieval, we can convert the query snippet to some spectral feature matrix like log-mil or short-term Fourier transform matrix. Audio is then represented as a T-length sequence of f-dimensional features. We convert each snippet in the database to feature matrices as well. Now, the metadata corresponding to query is retrieved as the metadata of the database snippet with whom the DTW similarity score of the query is a maximum. Here we see the spectrogram of a recording, and to its right, a noisy version of itself. As we can see, this approach is not very robust to noise. Hence, it won't give any good search result. Shazam converts the query and database audio snippets to spectrograms, but performs the search in a witty way. It uses peak detection algorithm to detect peaks in the spectrogram and then generates hashes with pairs of peaks. The spectrograms are converted to constellation maps of peaks. In the constellation map, we select a subset of peaks as anchor points. In the figure to the left, as you can see, the x-axis is time axis and y-axis is frequency axis. Now each anchor is assigned a target zone in the constellation map. Now say we have k points in the target zone. We generate k hashes encoding how the k points are present in the constellation map with respect to the anchor point. Let our anchor be T1F1 and one of the target zones point be T2F2. We generate a hash signature, which is a vector containing the anchor frequency T1, the target frequency, the anchor frequency F1, the target frequency F2, and the difference between the time locations, that is T2 minus T1. We also add the anchor time location to this hash signature vector as well. Although we won't be using it for measuring the similarity between two hashes, we will it will be made clear as we progress why we need the start time indices of the anchor points. Now the query is converted to a set of hashes. and each database snippet is also converted to a set of hashes. We can perform the retrieval as given each query hash, we find the closest hash in the database. Now we have k query hashes, therefore we will get k top hits. We can then choose the metadata we need to output by using a majority voting scheme over the metadata corresponding to the k matches. But such a search doesn't consider the time offsets in each hash. Shazam performs approximate nearest neighbors to get a set of matches for each query hash. Now each hash tells us how a pair of peaks are lying with respect to one another. It might happen that the query hashes are also observed in some other snippet not related to the original song to which the query corresponds to. But the order of the pair of peaks corresponding to each hash is different from that in the original song. As you can see in this view graph, the hashes generated by taking the green points as anchor would be the same for both the songs, but the order of those anchor points are different. We will now need the start times of each anchor point to perform fine-grained search of the query metadata. For each of the k query hashes, say we have r nearest matches. We can now sort all the matches for each of the k queries based on their similarity scores. This will in turn form a ranking over the metadata corresponding to the matches. From the metadata, we can form a ranking over the song IDs, and then we only consider the top 4 song IDs to perform fine-grained search of query song. For each song ID, we find all the matches corresponding to it. We then plot the set of points where the x coordinate is occupied by the start times of the query hash and y coordinate is occupied by the start times of matched hashes on the database corresponding to the song ID. Assuming that the query has more or less the same tempo as the original, we should observe a line in the plot corresponding to the original song. There may also be multiple lines in the case where there is a repetition of the same segment in the same snippet, but we should observe a line. We can use simple image processing techniques to detect such lines in these plots of each of these top 4 song IDs. Now the pros of Shazam are, it is robust to noise as we are detecting peaks and forming constellation maps, and it is fast as the hashes are only 3-dimensional vectors. But its cons are, it requires the query to be a noisy version of the original only. So it won't work for query by humming, where the source of the query is absolutely different. There won't be all the accompaniments present in the original song as well. The query may also differ in pitch, timbre, and tempo. An approach suitable for query by humming will be to do the search over melody than the spectral peaks. We will convert query and database audio to sequences of discrete note or pitch values, which we call MIDI note sequences. This can be done using melody extraction algorithms like Melodia or pitch extraction neural models like Spice by Google, the links to which I have provided in this slide. The MIDI note sequences can be compressed to note sequences, which are sequences of pitch value and its corresponding duration. After converting the query and database snippets to note sequences, the retrieval can be done via DTW search over note sequences. The note sequences are useful when, say, a trained person is singing. But for the case of humming, the melody may be pitch shifted from the original song melody, but we can understand what song it is by the relative changes in the pitches. Hence, we convert the query and the database audio to relative note sequences and perform the DTW-based retrieval, which we perform for note sequences. Here we provide an example of how a relative note sequence for a given note sequence looks like. Your note, the relative note sequences encodes how much the pitch changes from the previous note and the duration of the current note. You can refer to this paper for more information regarding a node-based query by humming system. In the next talk, I will be presenting the algorithms and models used by Google Now Playing, which is a state-of-the-art audio retrieval system made by Google and available in the new Pixel phones. Thank you.